Hi, everybody, and welcome back to CAD for Electronics. This is CAD 2131 and CAD 1133. So today we're going to dive into week number 4, lab number 4, and it's a bit of a doozy. There's a lot of stuff going on, a lot to cover, and basically I want to bring your knowledge up for a few devices, as well as show you a big one, which is how to create your own uh, footprints and components. All right. So hopefully everybody did well with last week's test, and you're feeling comfortable as we move along. So, what is an analog signal? As opposed to a digital signal where we would have a 1 or a 0, an analog signal, it basically ranges between 0 and some voltage, either positive or negative. And it comes in a couple different flavors. There's a frequency or pulse width modulation, where we would look at the duty cycle of how long it's on, or how quickly it turns on and off. And the other one is amplitude, and so we can see that we could be measuring either the voltage or the current, the amperage of how strong a signal is, as a representative of the signal. So, for example, uh, we could look at a light sensor and be able to measure the voltage from the light sensor and say that the brighter it is, the higher the voltage. All right. Quite often in industrial settings, we see frequency analog sensors. Frequency analog sensors are great because they're less prone to noise interference over long distances. Any degradation of the voltage is somewhat irrelevant when what we're looking for is a frequency. And so, great sensors for that would be pressure transducers or proximity sensors that we're measuring how far something is away. And so, if you can imagine, kind of like a sonar, so it sends out a blip, and when it comes back, we measure the time of flight, or how long it takes to leave the emitter and come back to the sensor. And so this would be a very simple frequency dependent example. All right. More prevalent for onboard stuff, so on your circuit board, would be amplitude voltage sources. So in this case, we're looking at a TMP36 in this example. And the way this works is uh, we have a voltage, a ground, and it just outputs a signal that is linear to the temperature. Now, this has some issues. The biggest one being over distance. Obviously, there is resistance in the wires, and so we're going to get a degradation of that signal across long distances. So, being able to measure very close to this device is a good thing. And the other problem is that RF signals can start to interfere with it, and so our measuring device is going to pick up any radio signals that are coming into this wire. So it becomes important to shield it and make sure that it's filtered properly on the sensor side. Uh, More prevalent for off-board applications is a 4 to 20 pressure transducer in this case. So as the pressure increases, the current uh, increases as well. And so we have a resistor called a sense resistor that's on our circuit board, and this device will adjust the voltage to give it the exact current that it wants, somewhere between 4 and 20 milliamps. And 4 is a great number. This actually works out very well when you pick that current sense resistor. But it means that if you don't see that 4 milliamps, you know that there's a problem with the sensor or the wire. So if ever you see 0, you have a problem. So it has a built-in fault detection. The other great thing is, no matter what's happening with that that wire, whether whether it's a kilometer long or a meter long, the voltage drop across the wire is somewhat irrelevant because we are, again, looking at current, and current is independent of resistance, right? It's going to drive the proper voltage. The downside is that you need a slightly more sophisticated sensor, and you need higher voltages to drive this. Obviously, you're not going to drive something at 4 to 20 milliamps with 3.3 volts. I don't believe they have them at this point. Ever growing in popularity are digital signals, digital sensors, and they have the advantage of actually doing all of the calibration and calculations ahead of time and just outputting a value in a digital format. And some of them use protocols like SPI or I2C so that it can communicate directly with the microprocessor, while others have external protocols like RS485, USB, RS232, or even TCP/IP, so they can talk directly to the internet. And these have a wonderful advantage that they can communicate over very long distances, whereas the I2C or the SPI should really be kept on your circuit board for, again, noise issues. But because RS485, for example, has a buffer, it drives a much higher voltage and is not prone to the same noise issues. And so think about, when you're designing your system, how you want to communicate with your sensors, and how far away, what environment it's going to go through. All right. So I mentioned earlier the TMP36. In our design, we're going to use a MCP 9700 or 9700A. And I want to talk to you a little bit about this because, as you can see here, it has a reasonably linear curve to it. Okay, but we need to understand what it's outputting. And so in this case, the ratio is 10 millivolts, okay, per degree centigrade with an offset. Okay, you'll notice that at 0 degrees, okay, we need to offset 0.5 of a volt. And then as we move across, we go up 0.01 for every degree. And so the math is fairly simple, but we need to understand what that's doing for us. And so here we go. Here's the actual formula written out from the data sheet. And there's a bunch of information that we can pick up here on the data sheet. One is that it is capable of running down to 3.3 volts. Okay, it'll actually go down to 2.3 and can go as high as 5.5, which is ideal for us. And one of the other things is to include a 100 nanofarad or 0.1 microfarad capacitor to prevent interference and noise. Okay, and so that comes from the data sheet, and we want to actually place it here across our VDD. Adding further capacitance here to the output is possible, but you want to be sure that it's very small because it will add hysteresis or a delay in your signal. So let's follow along here. We're going to take our lab from last week, and I want you to insert a TMP36, and we're going to wire this up. Here we go. So we want power here, and we want our ground here. We want a capacitor. We want to set that capacitor to 100 nanofarads. We want to set that to here and here. And we can drop in a voltmeter, DC voltmeter here. And if we run our simulation, you'll notice that it outputs a voltage. And so let's grab a little calculator here, and we'll actually do a little comparison here. So I have 850 millivolts minus 500 millivolts divided by 0.01, right? Because it's 10 millivolts per, sorry, not divided by 10 millivolts. Okay. And we get 35 degrees Celsius. So our output actually matches our input, which is fantastic. And so, sorry about that again. So let's grab one more component here, and I'm just going to talk about something real quick. Let's grab the MC9700A, and you'll notice that it doesn't really have, it doesn't show any other pins, okay? But it operates the same. And if I double click on it and edit the properties, you'll notice that there's a button here that is called Hidden Pins. Know that it is actually connected to ground and VDD. So if we use this instead, basically you could substitute, or you should substitute, this directly, like so. We'll change this to 35 volts. Current temperature 35, and say run, and we get the same value. And so it looks a little bit strange that nothing's connected here, but know that it does work the same. And this is actually going to be the chip that we use in our final product. So you could drop this in. It's okay to use it. There's no problem there. But we do want to change the footprint at some point from this SC70, which I love that little package, but we want to change it to a TO92 case. TO92. TO92. Perfect. With 80,000 pitch. I like it. We'll say okay. I don't know why it keeps binging at me, but there we go. All done. Okay. So that's updated the footprint, and we actually have the part that we are going to run in the end. If you don't change it over today, we're going to change it over at a later point. All right. Perhaps one of the most simple digital inputs that we could have is a simple switch, and you can imagine that that's either going to be a 1 or a 0 at whatever logic level you want. And so as digital goes, we move up from there. And so what we're going to look at today is something called a rotary encoder. And one of the problems that you're going to have is that Proteus doesn't have a simulation model or a footprint for the encoder that we want to use. And so while there is a tool that I'm going to show you later on how to import parts from the internet, if you can create your own custom footprint, then it means that you can do things like create daughter boards or your own personal components that may not exist anywhere. Okay. So let's talk first about what a rotary encoder is, and so that we understand why we would want to do this. So a rotary encoder is basically it's a switch or a pair of switches that, as you turn it, there's an optical beam that gets broken, typically by a engraved piece of glass or plastic, and so this creates ones and zeros as you turn it. And as you can see from the little example here, it's able to pulse, okay? And the faster those pulses come, the faster the computer knows that you're turning it, okay? And as you can see from this example here, there's a blue line and a yellow line, and depending on which is leading, we can tell whether it's going clockwise or anti-clockwise. And so this seems neat. Why would we want this? If you think about your car radio, so perhaps an older car radio had a knob that would be limited for the volume. You would hit an end stop and it would be uh, muted. You'd go all the way the other way and it would be at maximum loudness. These used something called a potentiometer or a rheostat, and they were great and still are great for doing things with analog circuits. But now that we're in the digital world, uh, to use them requires something called an analog to digital converter, the same as we have on our temperature sensor. And that's okay, but it does take time and it's susceptible to some noise. Whereas the rotary encoder, if you think of the knob to adjust the radio station on your radio, you can twist it forever and you never really hit an end stop. And that's because it's just simply sending pulses. And once it reaches a maximum value or a minimum value, it's done. It's hit its limit. And you can turn all you want. It's not going to do anything. These tend to also be more robust because there's nothing mechanical actually happening. So we don't have, in the case of a potentiometer, a wiper running across a piece of carbon on a disc. Okay, so as far as longevity, much, much longer. Okay, so in this case, though, we don't have the part available to us in the part library. And so we want to actually create our own footprint. And this is going to be one of the few cases where we'll do that. And we're going to also create a symbol for it. Okay, so something for the schematic, something for the PCB, and then later I'm going to show you how to create something for the simulator. All right. The first thing that we're going to do is we're going to create a rectangle. This rectangle is going to be something that can be resized later, but it's going to be the base of our symbol. Now, the one thing with Proteus is that it does things in layers, but unfortunately, we can't change the layer structure. So whatever you draw first is going to be on the bottom. Whatever you draw last is going to be on the top. So we have to think this through a little bit. For example, if I drew my little circle here first, I wouldn't be able, and I put this over top of it, I wouldn't be able to see any of this. It would be underneath. So let's, I'm gonna So let's create this symbol together. I'm going to follow along on my drawing, and you can feel free to pause the video as you move along, and we'll make this part together. All right. Okay. So the first thing that I'm going to do is I'm going to go over to my 2D graphics mode, and I'm going to make sure that I'm in component. I'm going to zoom in here a little bit, and I'm going to create a box. And as I say, the box can be resized later, so I'm not too awfully worried about it. And then I'm going to create a circle here. And, again, it's just a matter of making it how you want. Okay. I'm going to make it this big. And I'm not happy with it, so I can take it and I can move it around. There we go. And you'll notice that I can't quite get it in the center. So one of the things I can do is change my grid spacing, okay, so that I can move it to where I want. Okay, so that seems reasonable. How I'm changing my grid spacing is F2, F3, and F4. Make sure that you do set it back to the standard, which would be F3. So when you start to do your PCB layout or your schematic layout, however, because it really becomes problematic when you have parts that are offset. All right. So next I'll draw a little line in here just to show that I have, a detent in it. And I'm not happy with it. So I'll go down here to a smaller grid size. So Control F1. And I'll move this in a little bit. down one. And you can spend as much time on this as you want. Not really it's not really critical. Maybe I'll make a semicircle here. And if I wanted, I could go so far as to make the lines like I did previously to show that this is something that rotates. And one other thing I could show you is perhaps I want to indicate that this is just not really not really part of the actual structure. You could um, change the color, change the line type. Lots of parameters we could change. But let's go in and we're just going to edit the style. In this case, we're going to change the line width down a little bit. Let's make it 8 thousandths of an inch. Okay, see if we can get two of them at once. No, it's going to make me do it one at a time. Oh, let's see if I can do it this time. So Control 2, Control 3. I got all of them. Okay, so we're going to edit the properties. Edit style, all tagged. Oh, shoot. Try it again. Edit properties, edit style. Change it to 8 thou. And we'll get all tagged this time. Hey. All right. And as I say, if the grid ends up being too big and you're not happy with it, you can always resize it. But again, keeping in mind that once the part's been created, you can't really edit the layers. Okay, so next we want to actually lay in some pins. And so what we're going to do is we're going to come over here and we want to choose the device pins mode. Okay. And one thing to be really aware of, you'll notice that there is a little X on the outside here. We need to make sure that that X is on the outside of our part. Okay. The reason for this is that it's where the wire is going to connect. All right. And you may want to rotate this around, but my suggestion is to actually mirror it. And the reason being is that the where we end up with a part label is going to depend on the ultimate position of this. So top is top, and if we rotate it around, then the labels end up on the bottom side. Okay, so we have our 5 pins. So they would be the 3 for the encoder, 1, 2, 3, plus 2 for the internal switch, which this one has. You'll notice that the ones without the internal switch only have the 3 pins. Okay, come on, focus. And they do not have the internal switch. Okie dokie. So let's put some labels to this. And so what I'm going to do is I'm going to double click on it, and it's asking me for a pin number and a pin name. Before we get too awfully excited about naming these pins, let's take a look at the actual data sheet and make sure that we put them in a logical fashion. Okay. And so here we are. We're looking at the actual pin layout. And so we have pin A, B, C, D, and E. We might as well follow that same naming convention. Okay. And so this is going to be, today we're looking straight down at the part, which is nice. Sometimes they show us the bottom of the part, which is less useful. Okay, so we're going to be A, B, C, and then here we're going to be D and E. So easy enough. So pin name is going to be A. We'll call this pin 1. Next is B, and this is pin 2. And notice I'm just pressing next. You can also use page up and page down. Okay, so this is pin C, and pin number is 3. We're up here, so pin name D. Yep, D. And we'll call that pin. Now, typically it's 1, 2, 3, 4, 5, but we'll just keep things simple here. 4 and pin E, and we'll call that number 5. All right. Now, if we were to instead of having this as mirrored, if I unmirror this and we wanted to rotate it around, you'll notice that it puts the pin number on the bottom instead of the top. It's a small thing, but it's something that I like to see myself. It's, completely up to you if you want to do it differently. All right. So now we have our schematic symbol pretty much finished, but if we had a custom footprint, we wouldn't have anything to associate this with. So rather than create this and having to come back and modify it, we're just going to set it aside for a second and go create our custom footprint. Obviously, if we had a standard package, we could carry on and just not worry about this next step. But no. So let's go to our PCB layout, and we want to find a blank spot, some place that's devoid of anything, so that we can draw freely. Okay, so basically what we're going to do is create this bit of geometry here and make it so that it basically falls in, if you would. And the idea is that the manufacturer has told us what they feel is an adequate footprint for their part, and so we can kind of follow along with maybe a couple little exceptions. The first exception being I'm not drilling a square hole in here. While they could mill something in here, it would be cost inhibitive. So we're just going to make a hole, which will be easy enough. But what we want to do is make sure that we have a hole that's going to be big enough. And so what we want to do is calculate what the minimum hole diameter is going to be. And so if we assume that this is 2.1 by 2.1, which I realize it's not, we can simply take the hypotenuse. So if I say 2.1 millimeters times 1.414, which is the 1 over the square root of 2, it gives us just under 3 millimeters. And so I'm going to create a 3 millimeter hole here in the center. All right. Now I've gone and created instructions, sort of step by step on how to create this, and so I encourage you to just follow along. It's going to save you a lot of time and hassle and math because I've already done the math for you. So let's start by assuming that your origin point is occupied by something. So we're going to create what's called a false origin. Okay. And it's this button up here, and I will place it here randomly. All right. The first thing that we're going to want to do is to create those 3 millimeter holes. And I'm going to assume that you do not have a pad that is going to be sufficient for this. So what we're going to do is we're going to go over to round through hole pad mode. We're going to create a new pad. And this time I'm going to call this, let's say, I call this 3.5 mm by 3 mm. Okay. I'm going to make sure that it's circular, and the rest of it I don't really care about right now. And I'll say, okay. And it's asking me for a bunch of information. So we're okay with the title, but we want to start to set this out as our specifications. And so in this case, the drill hole is going to be 3 millimeters, and the diameter is going to be 3.5 millimeters. Okay, the drill mark we're not going to worry about too awfully much, and the guard gap we're absolutely not worried about. And I'll say, okay. And you'll notice now over here that I have a new hole that's called 3 mm by 3.5 mm by 3 mm. And we can place this hole and at a specific location. Okay, and the way to do this easily, rather than trying to follow around the location, is to just place it anywhere, and then we will move to the location we want. And in this case, we want it moved to negative 7.4 and 0. Now, one of the things that we can do is we can actually edit these properties to be only a drill hole. Okay, and by having a drill hole means that we don't have the pad around it. Okay, in this case, we could do it, but one of the other things that we can do is not plate the hole. Okay, and this was, I thought plating holes would cost more money because it would take more copper. But as I found out from a board manufacturer, they actually charged me more money to not plate a hole because they had to deal with it in the second operation. So these days I don't bother not plating a hole. And in this case, we can leave the just the drill hole. We don't need the pad around it because we're not going to solder to it, or we could actually just leave it as is, because there will be plenty of room around it to not worry about it. All right. So know that you can change it, but it's not necessary. Okay. So now we need to create a second one. And so again, we can do we could put in another hole, or we could do a block copy. And again, we'll just move it to, in this case, positive 7.4. And that's fantastic. Or we could have used the offset, which works as well. So let's try that. So we're going to highlight it. We're going to replicate it. And in this case, we're going to move, instead of 7.4, 14.8 millimeters to the positive. And we'll say, okay. And so there we have our two holes, which are for the these little guys here that will hold it from rotating if there's any friction. One thing we don't want to do is rely on our solder points here to do any mechanical holding. All right. So next we want to place the 50 thou by 100 thou pads, and the first location is going to be minus 5 millimeters by minus 10.5 millimeters. So let's pick another pad. We want that was 100 by 50. Oh, there again, I don't have one. So let's create 100 by 50 because it's not hard. So C 100 by 50. And in this case, instead of 60 thou, we'll have 100 thou and our drill hole at 50. All right. So there's that. And note that it's wanting to place it as the drill hole. So we're going to want to fix that. So edit properties and all in this case. Okay. And let's move this guy to, that was -5 millimeters. Very important to keep the millimeters in there. And positive 10 point, no, negative 10.5 millimeters. All right. Looks good. And now we can replicate this one. Replicate. And in this case, we want a step of 5 millimeters. And we need 2 copies of it. Okay, the last one is going to be placed at negative 2.5 millimeters. And I'm going to say negative, no, it's positive 7 millimeters up. Okay. That doesn't seem right. Let's double check. 2.5. There we go. And again, we're going to replicate this over 5 millimeters again, but only one time. So we have the same pitch, just on a different center. Okay, next we can do some beautification. We can make it pretty. Basically, we usually add some silkscreen around the outside just to mark the edge of the part so that we know approximately where it is and to keep other components away. And so again, we can look at the data sheet and we can get some scale of how big this thing actually is. Okay, so we're about 16 millimeters by give or take 16 millimeters. So let's go back here. And a couple ways that we could do this. We could literally draw a rectangle in top silk that is 16 millimeters. So we went from 8 by 8 from this corner down to this corner. We'd be okay. But one thing that we want to avoid is having our silkscreen cut through a part. And so instead, what I'm going to do is I'm going to create some line segments, okay, that basically just sketch the outside of the part. So we'll call that reasonable. Okay, so the next thing is we need to label these parts. And as you recall, we actually took the time to make sure that our mechanical model was going to follow the data sheet. Okay, so in this case, our pin numbers we started with 1. So rather than doing it manually, what we can do is we can go into a tool that will automatically help us name these. So under tools, you'll see that the shortcut is N, so automatic name generator. And there's a couple little tricks with this, but we'll go through it once. Okay, so we're going to start with the string. and our count is 1, and we'll say OK. And you'll notice that there's a little equal symbol. So we can simply go around and click or press the space bar, or enter, I should say, to label these. So 1, 2, 3. And as I said, usually it goes 4, 5, but we did ours backwards. So 4, 5. And then we also have these two guys that we're going to put up here. All right. So to cancel it, again, I'm going to use N rather than go up to the tools, pull it up, and we have to cancel. Okay. So it's a bit of a pain that way, but it actually saves a lot of time, especially when you have a lot of pins to do. The other thing that we can do is actually change the pin number. In this case, we can call this M1 and M2 for mechanical, right? So we don't want to confuse these as real pins. Okay, so we're happy with our layout. We can then go to our selection mode and window everything to do with this footprint. And then we're going to go up to make package. And now we need to be a little bit reasonable about picking a name that we're going to be able to find. I'm going to call mine encoder 2021. And we're going to need to find some place to put this in our library. So we're going to put it in user package, and it's going to ask us to classify this so that it can help find it later. And so I'm going to put this down under miscellaneous today, and it's definitely through hole, and the rest of it I'm going to leave blank, and I'll say okay. And you'll notice over here now it actually says encoder 2021, and I can actually place this part now as many times as I wish. All right. Next, we need to go back to our schematic. Okay, so we're going to go in and to our selection mode. We're going to window all of our part. We're going to create a new device. And this time I'm going to call it ENC 2021. I'm going to use a prefix of SW for switch. Then we're going to go to add edit. And we want to add a package. And in this case, I called mine encoder. Oh, encoder. Okay, so spelled it wrong. That's not going to help. I'll say okay. And you'll notice that it automatically lines up our pin 1 through 5. And we have 2 pins that aren't connected. And so here I'm going to go under my NC, so no connect. I'm going to add M1 and M2. Okay. Then I'm going to assign the package. Next. We could link in our data sheet. Okay, I'm not going to bother right now. But under device categories, we're definitely going to have to put something in. And so I'm going to put in this case, what don't we do? Miscellaneous, and we'll leave it. And I'll say okay. And now we have something over here called ENC 2021. And you'll notice now when I go back to my PCB layout, so I do have my encoder footprint. I also have the encoder SW1. Okay. And so this is a great way to create a part. And you can see that once you're familiar with the process, it's actually fairly easy to create the footprint. And so don't be afraid to use parts that may not be available in the library. All right. Okay, so now that we've created our footprint and our package, we can go ahead and wire this into our system. And so basically we have 3 pull-up resistors. So you'll notice these 10K resistors are pulled high, so to VCC, and basically they'll make sure that we have a nice strong signal. Okay, so basically when they go low, okay, they get pulled low here, they'll give the signal to the microprocessor, and we want to connect them uh, like so, with the exception that I just noticed here. E1 obviously is not going to get connected to the same place as E2. Do connect that appropriately to one of them goes to pin 2. Okay. So basically, what I wanted to do originally was to print this off, but you don't need to. You don't need to sign it off to me this week. So don't worry about this next slide. We'll move on. But what I do want you to work on for your homework assignment for the lab is I want to create this RS232 circuit. Okay. It shouldn't look too awfully daunting, but do take your time. Make sure that you lay it out exactly as I have here. Okay. Unlike here, don't lay it out like this, but do lay this one out as drawn. And I also want to show you the grouping function. One of the great tools that we have available to us now is something called grouping, and so here I've thrown a couple of resistors at my encoder, and I have some other resistors that are not part of my encoder. And so one of the things that we can do is assign a group, if you will, and this isn't to be confused with a group like we have in AutoCAD where things are going to actually be tied together, but it's a way for us to uh, give some indication, okay, that these parts are of a subassembly. So in this case, uh, we we can take all of these and say that this is part of the uh, encoder subassembly. And so what we can do is under Tools, we have the Property Assignment tool, which is the shortcut is A, and we can type in, and it is case sensitive, um, but I'm going to put in a curly brace group equals encoder, spelled properly this time, and end curly brace, and I'll say okay. And it doesn't look like anything's happened here, but if we go into a part, you'll notice that it's actually written in here. We've actually assigned a property. Okay. And so what does the curly brace do? You'll notice if I take the curly brace out, it actually shows that text. And so we definitely don't want to have our drawing all covered in this group thing. Okay. So what does that do for us? When we go to our PCB layout, you'll notice that basically all of these parts are headed under encoder. And so I can go through all of the encoder parts now and select those parts. Okay, so it's a great way to organize all of your components without having to sort through. Was R4 part of the encoder circuit, or was it part of another portion? And so, great way to organize your schematic for your PCB layout. And so, when you're doing your lab assignment, I really want you to think about the groups and start breaking things up, because next week we're going to do the PCB layout. All right, so the next thing that we want to do is change the size of the PCB one last time. I promise it's the last time. I'm not going to make you do it again. The final board size is 62.5 by 100 millimeters. And so go ahead and change that. All right. The next thing that we want to do is we want to we want to talk about creating different grounds, different areas on the circuit board. And previously we had talked about creating silk screens and breaking things down into smaller portions. And I talked last week about having the ability to isolate the power supply so that we could test it or substitute a different power source. But one of the things that becomes a real issue with more complicated designs, especially, is ground planes around high noise devices like your power supply. And now this is a linear power supply, so it's not the end of the world. This is more of an academic exercise, but it's a really good idea to have a separate ground plane for your power supply. And so next, we want to actually create our own little ground plane that's going to go around just the power supply. Okay, so last week we talked about creating a ground plane, and that's fantastic for all of your parts. So we'll do it one more time. Let's go to Tools, Power Plane Generator. We want it connected to ground equals power. And we'll say OK. And you can see my entire design here, and everything's connected except my power supply. And the reason why my power supply isn't connected is because we want to go back to our schematic. Let's go to your power supply, and we want to actually change, that label where we put in PSU equals ground. We want to change this to PSU GND. And so literally double click on it. If you didn't put one in the first place, you can right click and place a wire label. And in this case, you're going to type in PSU GND. Okay. And I have class equals PSU ground. Just leaving it as power should be sufficient. And there we go. Okay, so when we go back to our PCB layout, what we want to do is we want to create a ground pad that's only in this area. And so the way that we do that is this tool over here, zone mode, which you'll notice looks identical to this one, Power Plane Generator, but they definitely react differently. Okay. And so I'm going to come in here and I'm going to create, lay that down like so. Here we go. Fantastic. And rather than putting it as ground equals power, we're looking for PSU ground, which we just created. Okay. It's on the bottom, and we'll leave the rest of it for just now. And you'll notice that it's actually created a separate ground plane for all of these items. Okay. So when I remove this jumper, it'll actually isolate this ground from this ground. All right. And this is important again for noise attenuation when we have switch mode power supplies. Today it wouldn't make a huge difference to our design, other than it would allow us to actually fully remove the power supply if we had an issue. Once you have your new ground plane placed, I want you to manually route all of your power supply. You can make it look similar to this. That'd be great. And the next thing is to actually start to lay out the rest of your PCB. And you'll notice that I have my encoder down near my microprocessor. I've moved my microprocessor over. We can drop in some mounting holes. We've got your thermal sensor placed now, and the RS232 that you're going to create. And once you've manually laid out your power supply, you can go ahead and use the auto router to lay it. and then you can clean it up a little bit. But don't spend a lot of time cleaning it up, because we're going to erase it again. And that's pretty much it for this week. It's been a fairly long lecture and a lot of new material. A lot of people struggle with creating a footprint, but it's important to be able to do it, or at least understand that just because it's not in the library, we can still use a part. All right. Questions, comments, suggestions, please feel free to send me an email at any time. I'm here to help. All right. And hopefully, again, you're enjoying this course and learning a lot about how powerful Proteus is. All right. Well, thanks, everybody, and have yourself a great day. All right. Bye now.